So what does the seafloor look like? Well, it turns out that for a long time we thought the seafloor was flat and that nothing really interesting happened there. It wasn't until a geologist who was in World War II, who taught at Princeton, wanted to take this Navy technology and the sonar capabilities and scan the seafloor and see what was going on. Turns out there's a lot going on down there. So in the middle of our Atlantic Ocean, and we're going to reference the Atlantic in this class because that's the one that's closest to us, there's a mid-Atlantic ridge. We know that's roughly in the middle of the Atlantic, hence the name. And we know that at that plate boundary, it's divergent. How do we know it's divergent? Well, we see it's a long chain of volcanoes and that it's pushing North and South America away from Europe and Africa. Is it going quickly? Nope. It's going at about the rate that your fingernail grows, about 5 to 7 centimeters a year. Now, some plate boundaries are super slow. They go to 1 or 2. Some go at 20. Ours is about 5 to 7. What we see there is new seafloor being created. It's the youngest seafloor. And because it's literally coming out of the volcanoes that are underneath the Atlantic Ocean and forming this igneous rock, well, eventually it's going to push it away and push it towards the continents. So we can take samples of this rock and we can take evidence that we see going on there and at other plate boundaries. And we know that the oldest rock is at the continents and the youngest rock is at the mid-Atlantic ridge, or whatever that divergent plate boundary happens to be called. We can also take samples of the seafloor and check out Earth's magnetic field. Now, you would think, well, that doesn't make sense. Why would you do that? The north is the north and the south is the south, and we have GPS and magnets. Why are we wasting time on that? Well, it turns out that's not always true. It will be for our lifetime, and it will be for a lot of people's entire lifetime, because these take thousands of years to change. And even if it was going to change, it's not like we're going to wake up one day and north is going to be south and south is going to be north. If that happened, we would be in a lot of trouble because pretty much anything that relies on magnets or electronics would stop working the way we expect them to. We can see that these flips have happened in the past, but we don't know why, we don't know how, we don't know what it's related to. But it's important to know that what we call the geodynamo, all the spinning of Earth's cores and the magnetic field that goes along with it, is a complicated thing. We're still trying to study it, and we're actually tracking magnetic shifts right now that don't line up to our predictions. Why? We don't know. We're still trying to figure that out. So what does happen? What can I tell you about that isn't just some hypothetical, stuff that geophysicists are trying to discover? Well, I can tell you what happens when the continental and oceanic plates run into each other. This is called an oceanic continental convergent boundary. Now, remember when I said in the last video to remember the density, that continental is 2.7 grams per centimeter cubed and the oceanic is 3.0 grams per centimeter cubed? Well, if you didn't, it's come up again, so maybe take note of that. What happens is hopefully obviously to you, the less dense material is going to stay on top of the more dense material. And in this case, the more dense material is that mafic oceanic crust. It's going to get pushed under and get recycled, as we talked about with the convection currents. However, not only does it just get recycled back into the mantle, some things happen. We get earthquakes. These deep, pretty large earthquakes can happen at these boundaries. We see magma being pushed up through the continental crust, and if it goes far enough, we happen to see volcanic arcs, these land continental-based volcano chains, and we have some in the US. Go look at the West Coast, and we're going to talk about it, and it's on your reference sheet. Mount St. Helens is one of the most famous examples. That's part of it here in the United States. We also can understand that these subduction zones are when the oceanic crust gets pulled under. This is called slab pull. Now, I don't know if you need to know that or not, but I'm telling you anyway. It also doesn't really make sense. It forms these little tiny trenches between the continental and oceanic plates. We don't typically think, it doesn't make sense. You think trenches would happen when it gets pulled apart. Turns out trenches happen when they get pushed together. So, what else do we need to know? What other kind of boundaries do we need to know about? Well, we talked about the Oceanic and Continental convergent boundary. What happens when two of the same thing run into each other? What happens when a continental runs in together? This one's kind of more simple. It's kind of easier to guess. Two of the same thing hit each other, they fold. So two of the same thing, two continental run into each other. What are they going to form? Mountains. It's because the density doesn't change, and unlike we're going to see an oceanic convergent, nothing is really changing the density of these either. So one doesn't really go on top, one doesn't really go underneath. They just hit and bend enough and over enough time and enough pressure, you get mountains out of it. This is how the Himalayas and Mount Everest were formed. In a similar but slightly different process, when two oceanic plates run into each other, one of them typically, because of a bunch of different processes and how the heat is transferred through the magma and the water sitting on top of it and where it's at and what's going on, one of them is typically less dense and warmer. That's going to be the one that stays on top. The more dense and cooler one is going to get pulled underneath. We're going to have another subduction zone. But there's no land to form volcanoes on this time. So what is it going to be? Well, it's going to start forming these underwater volcanoes. But if the volcano and the igneous rock stacks up enough and we have enough material, we can get islands. This is not how Hawaii is formed. We're going to talk about Hawaii later. This is not how Hawaii is formed. It is, however, how Japan was formed. And that's why, if you've ever visited Japan or you want to, or you know anything about it, you'll know that Japan has a lot of volcanoes everywhere. Well, it's in one of the most tectonically active places in the world, and it has a lot of earthquakes because of that. And as you remember, hopefully remember from the energy sources when we talked about the tsunami, they have tsunami warnings there pretty frequently as well. You know, it's not like it's an everyday thing, but it's way more than a lot of places besides, islands in the middle of the ocean might get them. So what else do we look at then? Well, we have different types of convergent. We haven't talked about divergent yet, but, well, we talked about it in the sense of the Mid-Atlantic Ridge. We're not going to get into super detail here with the divergent, but the last one is transform. And as I told you, it's kind of like the strike-slip fault that you might remember. We're also going to call them shear faults. But what's going on? They just go beside each other. They're not going towards each other. That's convergent. They're not going away from each other. That's divergent. They are just going beside each other. That's called a transform boundary. Nothing happens here in the sense of nothing is created, nothing is destroyed. However, we do get shallow earthquakes. Remember that. Shallow earthquakes. Convergent and divergent can create these large, deep earthquakes. Now, transform can still create some pretty large earthquakes, don't get me wrong. But even if it's not as strong, the thing with transform is that the earthquakes are closer to the surface. And even if they're not, a magnitude 7, if they're magnitude 5.2, let's just make this up, but it's 40 kilometers closer to the surface, it's got a greater chance of doing some damage. That's what California has to worry about because they are sitting on a strike-slip fault with the San Andreas. They're sitting on that transform boundary. So their earthquakes aren't necessarily huge, though they certainly can be. The fact is, a lot of them are fairly close to the surface, and we consider close to be anything under 70 kilometers or so. That sounds like a long way, and it is a long way. 70 kilometers, if you want to look it up and convert it to miles, I'll put it right here. It's pretty close to the surface when some other ones happen at 200, 300 kilometers below. That's a lot closer. So, what do you need to know from this part of it? Make sure that you can read the reference tables. Now, at this point, I haven't really referenced the map that you have as part of your reference tables. We're going to go over that, don't worry. But if you get confused on what the boundaries are, they're right there. It shows you where they're located. It shows you some basic information about them. Also, look at those plates. See how many different plates they are, and think about what the plates actually make up. Is it oceanic? Is it just land? Or is it both? Figure it out.